Okay, so Chapter 4 is about forces and motion. And so basically the concepts of force and net force are one of the main things we're going to talk about. We'll also talk about inertia and Newton's first law of motion, his second and third law of motion. And then we'll learn how to represent motion and forces by using what we call free body diagrams and translational equilibrium. And then lastly, we'll talk about friction. So for 4.1, a force is something that is compatible of, or is capable of changing an object's state of motion, that is, changing its velocity. Any particular force may not actually change an object's state of motion, as there may be other forces that prevent it from doing so. However, if the net force, the vector sum of all forces acting on an object, is not zero, then the velocity will indeed change. And so in this picture, what we see here for part A of this figure, you see two men on the opposite sides pulling. So the vector represents the magnitude, the length of the arrow represents the magnitude of the force, and then the arrow points which direction the force is being applied. So this gentleman is pulling in this direction to the left, and the green gentleman is pulling to the right. But because their vectors are equal in length, or equal in magnitude, they cancel each other out. So the net force is zero, okay? And so when there's zero net forces, there's really nothing that can move. But when we see part B, if the gentleman in the green pulls a little bit harder than the gentleman in the red, what will happen is that the object will obviously move this way. And so I guess this would be a good good time to point out that forces are vectors, and we could represent those. Remember that a vector has a magnitude, which is the length of the vector, and then it has a direction, which is the direction in which the vector is pointing. And so if we take the sum of the vectors, for example here from part A of this figure, because the vectors are equal in magnitude, in other words f sub 2 minus f sub 1 equals 0, then no motion is taking place. However, if we take the sum of the two vectors from part B here, actually part C, I'm sorry, what we'll see is that the resultant vector, or sum of the two vectors, because f sub 2 is greater in magnitude, well then we have motion in that direction. So the resultant vector, the force net of the vector, is the difference in these two force vectors. So we distinguish two types of forces. Contact force, which is a push or pull, and this could be represented by friction, tension on a rope or string, somebody pushing something with their hands or pulling something. Those are examples of pushes and pulls. And then there's a force that acts at a distance. And these are usually associated with fundamental forces like gravity, magnetic force, or electric force. For 4.2, inertia and Newton's first law of motion is based on force to some degree. So according to Aristotle, the natural state of objects was to be at rest. And if you got them moving, eventually they would come to rest again. Well, that was his understanding on Earth, and he didn't really think about gravity of the Earth restricting motion. Galileo did some experiments by rolling balls down inclined planes and realized that in the absence of some kind of force, the object would keep moving forever once it got started. So basically, Aristotle's belief was based on friction and gravity. You know, if I roll a ball across a level plane, eventually it'll slow down because of friction and because of gravity. So Galileo called this tendency to be in motion, or tendency to stay at rest, inertia. So inertia is a natural tendency of an object to maintain a state of rest, or to maintain or remain in a uniform motion in a straight line, a constant velocity. And so later Newton, when he started to develop physics, he realized that the mass was a measure of inertia. So Newton's first law is very similar to Galileo's concept, and we call it the law of inertia. But basically it's like this: in the absence of an unbalanced applied force, In other words, the net force applied to an object is equal to 0. A body remains at rest, or a body at rest remains at rest, and a body in motion will remain in motion with a constant velocity or a constant speed and direction. So experiments show that the acceleration of an object is proportional to the force exerted on it and inversely proportional to its mass. The acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. The direction of acceleration is in the direction of the applied net force. So what that means is that force is really equal to mass times the acceleration. And since acceleration is a vector, then force would have to be a vector, where mass is a scalar. So the unit of force in physics, we call it newtons, and newtons is equal to 1 kilogram meters per second squared. And so here we have an example of force. I have a mass of an object. This gentleman's applying a force, and there is a mathematical relationship between the force applied and the acceleration of the object. Here, if you double the force, because the mass does not change, you double the acceleration. And here, if you double the masses but apply the same force, well, then the acceleration is exactly half. And this is based on this mathematical equation. An object's weight is the force exerted on it by gravity. So a lot of times when we talk about weight and mass, they're actually two separate things. Like most people kind of interchange them like they're the same. No, mass is the amount of stuff. Weight is the force applied to something due to gravity. So your mass is the same on Earth as it is on the moon, but you would weigh less on the moon. So here, g is the acceleration due to gravity. It's 9.81 meters per second. Weight, therefore, has the same units as a force, so newtons. We're used to thinking of pounds, which is another way to measure force. But in our class, we're going to call them newtons, okay? And so Newton's second law of motion may be applied to a system as a whole or to any part of the system, and it's important to be clear about what a system is. So let's just look at this picture. If I pull from this end, I apply a force to this block. This block will then begin to go in motion. However, m sub 2 will want to stay still. This creates tension in this direction, and it creates tension in this direction, but the overall system is accelerating in the direction of the force that's being pulled, the net force, I should say, because there's a lot of forces. And so we can illustrate this by creating what we call free body diagrams of each part of the system. But if I separate the system, notice that the acceleration of m sub 2 is equal to the acceleration of m sub 1. So Newton's second law of motion applies separately to each component of the force. And so basically the sum of all the forces in the x direction plus the sum of all the forces in the right direction is equal to the mass times all the accelerations in the x direction plus all the accelerations in the y direction. And so we actually have two separate forces, forces in the x direction and forces in the y direction. Now the vector mathematics is the same as what we learned with velocities and everything. So if I have a force in this direction, x, and a force in this direction, y, by using the triangle method, the overall force is the resultant vector from the tip to tail of the two component vectors. So Newton's third law of motion is for every action there is an equal and opposite reaction. And so what we're saying here is that if the force is going in this direction from point 1 to point 2, then it'll have an opposite and equal reaction, which will be the same amount of force applied, except it goes from 2 to 1, and it's in the negative direction. So if we look at this object, the block is pulling down due to its weight, but the table or substance that it's on is pushing up with what we call the normal force. They're equal and opposite. Now what is the normal force? Well, the normal force is the force that's exerted on an object to keep it still, I guess. So if I set a wooden block on my desktop, The block wants to go down due to gravity, but my desktop pushes up, which keeps the net force equal to 0. So this image shows a block exerts a downward force on the table exerts an equal and opposite force on the block, and we call that the normal force. So here's a couple different illustrations of that third law of motion. Here we see a guy who's holding a briefcase, and here are some free body diagrams of different components of the system. But the briefcase in this particular portion is not in motion, so it has no acceleration, and because it has no acceleration, the forces, the net forces, in other words, if I added all these forces together, they equal 0. But when this gentleman lets go, this F sub 1 force that's pulling up from his arm is no longer there, so then gravity takes over and it falls down. What does it fall at? At the acceleration due to gravity. The weight of the briefcase is the force. So we could represent these different forces by drawing the vectors on what we call a free body diagram. And so we focus on the center of the mass. So if we look at this block has the center of mass. It has a normal force that it's opposing it from falling through the inclined plane. It has a force of gravity pulling down on it. And in this particular diagram, it has a string attached to it that is attached to a pulley that is pulling from the mass or weight of this second block. So if we represented all the forces acting on this block, we could just simply draw a free body diagram. Now, notice this, and we talked about this a little bit in chapter 3. We can choose our XY plane and orientate it any way we want. So on inclined plane applications, we usually tilt the XY plane because it makes things easier for us to make the calculations. One thing I want to point out is that when this block is in motion, the acceleration is parallel to the surface of the inclined plane, and that's what we arbitrarily chose the x-axis to be parallel to. So a free body diagram draws forces of an object as though they're all act at a given point, and you should draw a diagram because it helps you to really think about all of the forces acting on an object. If an object is to be in translational equilibrium, there must be no net force on it. This translates into 3 separate requirements: that there be no force in the x, y, and z direction. Friction is just kind of a well, I mean, it's a reality of Newton's third law of motion. When you walk, you push against the floor, but when you push against the floor, shut that. When you push against the floor actually pushes against you. So in order for you to walk forward, your foot actually pushes backwards. And friction kind of holds your foot next to, kind of holds it on the ground, otherwise your foot would just slip. Static friction is a friction used to prevent motion. So, and then there's kinetic friction. There is a difference between the static friction and the kinetic friction. There's a little more force required to get an object moving if it's on a surface, and that's the static friction. But once an object is in motion, it doesn't necessarily need as much force to overcome it. So we call them 2 separate frictions because we measure the coefficients of both. And then rolling friction is a similar type of friction, but that's when you have a object rolling without slipping. There's still some friction that occurs. So we observe that a frictional force is proportional to the normal force for static friction. So static friction, this is this constant, I think that I got to remember, is that mu sub s? Yeah, I think that's mu sub s. Mu sub s represents the constant coefficient of static friction. So usually there's a number. It's like a percentage. It's usually a decimal. It's a very small number. And then the static frictional force may not have its maximum value. Its value is such that the object does not move and depends on physical circumstances. So basically what we do to figure out the static friction, like let's say a car. if I wanted to figure out how much friction would be generated by trying to drag a car across the pavement, or well, we'll just say a block across the desktop, that desktop is going to apply a normal force. So if I wanted to drag this block, what I would do is figure out what the static coefficient of wood it is and multiply that by the normal force that's exerted on the block, and that would tell me what the static force is. And the static force always goes in the opposite direction of the motion. And so we would calculate the kinetic frictional force the same way. We'd say mu sub k. Now this number is usually a little lower than the static frictional force, because once you get an object in motion, you don't have to oppose friction as much. And so in this illustration, what happens, and to show you what's going on there, with the static frictional force, the more that we apply the force to get the thing moving, eventually we're applying force, and the friction force increases, boom, the object's in motion. Once it's in motion, we just need to maintain that motion so there's less friction, okay, that we have to overcome. Does that make sense? And so here are some common coefficients of friction depending on both materials involved. So, for example, aluminum on aluminum has a static friction of 1.9, and then it has a kinetic friction force or coefficient of 1.4. So if the normal force was 10 newtons, then what you would do is the static friction would be 19 newtons. So you'd have to push 19 newtons to get a 10 newton object moving, but then once you got it moving, you would only have to push 1.4. So glass on glass, and so on and so forth. Now rubber on concrete, this is an interesting one before I move on to the next slide. This is how police officers can determine how fast a car was going. So if you slam on a brake and the skid marks are a certain length, they use this frictional force to calculate the acceleration, because remember, acceleration is mass times acceleration, or force is equal to mass times acceleration. So they figure out, they use this static and kinetic frictional forces on dry and wet pavement, and they work backwards to figure out what the acceleration or the velocity of the car was. So friction, this is a form of frictional force. It is an approximation. The actual phenomenon is very complicated and dynamic. The coefficient of friction may vary somewhat with speed. There may be some dependence on the surface of the objects, whether they're rigid or smooth, or so on and so forth. Also remember that these equations are for magnitude of the frictional force that is always perpendicular to the normal force. Air resistance is a form of friction, and it depends on the object's shape and size as well as its speed, but basically the object is traveling through air molecules. The air molecules push against the object and slow it down. For an object in free fall, there is a force of air resistance that increases as the speed increases, and eventually it equals the downward force of gravity. At this point, no net force on the object is applied, and it falls at a constant velocity, and we call that the terminal velocity. So if a human being jumped out of a plane at 10,000 feet in the air, at some point in time, the human being will not accelerate. They will just reach what we call a terminal velocity. Here's an example of that. I have an object which is a ball. I drop it, it goes into free fall. At first, the velocity vector is small. As acceleration due to gravity is applied, a force to it, then the velocity increases and the velocity increases. And so if we look at our velocity over time graph, the velocity increases and increases and increases, but due to air resistance, at some point in time, the body cannot increase in speed. This is what we call the terminal velocity. So a force is capable of changing an object's state of motion. That state of motion will change if and only if there is a net force applied to the object. Newton's first law, in the absence of unbalanced external forces, the object's velocity will not change. Newton's second law is that force is equal to the mass of the object times the acceleration of the object. The weight of something is the force exerted on an object by gravity. Newton's second law holds separately for each component of acceleration. Newton's third law, for every force there is an equal and opposite reaction force acting on the other object. There's a term called translational equilibrium. An object having no net force on it in any direction, its velocity will remain a constant at zero. So basically what this last portion means, and we need to think about this, if I don't accelerate an object, its motion remains the same. So if it's at rest and I don't accelerate it by pushing it with a force, then it remains at rest. However, if an object is already in motion and there is no resistance to that motion, or force, which is a form of acceleration, that means it's still in motion. So if we were in space and a satellite is moving and there is no resistance to that satellite because it's in the vacuum of space, that satellite will travel forever in a straight path and never change its velocity. So what I'm trying to say is it's possible to have an object that has a velocity but no acceleration. Does that make sense? So let's look at frictional forces. We basically take a coefficient and apply it towards the normal force. The frictional force is always perpendicular to the normal force, remembering that the normal force opposes the object's gravitational pull, but basically there's a smooth surface that an object is resting on, and it cannot move through that surface because the surface is applying a normal force, which is perpendicular to the surface of the plane or object that the surface that the object is resting on. Also, an object falling in air experiences air resistance. This resistance increases the object's, the air resistance increases until the object reaches what we call a terminal velocity. Okay, and that's it.